Hi, my name is Ottrum Brandt. I'm part of the coordination team of the HeSyn Research Data Infrastructures, and we do these HeFDI Data Talks every second Friday from 11 to 12 to tackle different topics concerning services and offers in the field of research data management. And we are very happy to have Arman Khalatyan here today from the Punch for NFDI consortium. Mr. Khalatyan, he's an astrophysicist at the Leibniz-Institute für Astrophysik in Potsdam, IP. And maybe you want to add a few words concerning your research background yourself. And we are very happy to have the physical science here today, because as I said before, when we talk to each other, it's very interesting to see a community which is very much apt to handle in the field of research data management and to provide data and to reuse data, because this differs a lot across disciplines. For some disciplines, this is very new to gather, to collect, and to share data. And for the physicists, this seems to be a routine, at least for other disciplines. So we are very happy to have an insight into the office of the Punch for NFDI consortium and how your services are adopted by the community. So I'm very happy to hand over to you, Mr. Khalatyan, and we are very keen to see your talk. Thanks.
Thank you very much for introduction. I will introduce myself a little bit more during the talk as well, what I'm doing. And this is, for me, is non-convenient talk that non-experts from our field are interested in this complex stuff, what we are doing. I'm happy to present stuff. You can interrupt anytime. I cannot see the videos or hand rises during the talk, but anytime you can interrupt me. So we have here this small room in Bonn University just before lunch break, because there's a parallel conference going on next to me. If there will be very noisy, let me know, and because I don't see your faces. And if something is wrong, just ping me. Okay, I will share my slides. I'm myself is from Astrophysics Institute Potsdam. I'm astrophysicist, and with Harry Enke, we are already colleagues since 2004, many years, and he was asking me to jump in and give his presentation, but most of the materials what we have is just collected from different groups or consortium members, so I will try to present this stuff as simple as possible. So what is this about? This Punch is opening for particles, universe, nuclei, and hadrons for the NFDI. Interesting thing is this: most of those components like particles, nuclei, and hadrons, and universe, they are working almost with the same type of the data, like petabytes or over hundreds and hundreds of terabytes. But the type and standardizations are totally different. I'm from the part of universe. Myself, I'm cosmologist. I was doing my PhD on black hole formation in cosmological simulations in running on high performance supercomputing centers. And recent several years, we are trying to build up some kind of interconnect between these all consortia and members and bring standards into the life. So who is inside this large consortia? You can see here many well-known universities, research centers, particle physicists, even Hochschule für Technik und Wirtschaft Berlin is inside. We have many groups involved, and we are almost over 130 people within Punch. And you can imagine we have very diverse community in terms of data handling and working styles. We have actually several working groups or task areas. Each task area has internal lower working groups, and most of for us, from our side, from AIP side, we are working on this user collaborations part in the middle, where this TA4 or TA3 or TA2 interconnections is happening, like how you organize your compute resources, how you access to your storage and bring them together, so-called cloud services inside, and then exchange the data. But this is quite very lightweight presentation of this situation, where you have scientists and he tries simply over something access this complex infrastructure. Just in a more simple overview, what we would like to have in reality, like hide from this scientist in this left upper corner, behind the portal. All this technical stuff should be hidden, and it should help him to organize his science and do not care where his jobs are running in some containers, or it's going in some, I don't know, hidden storage or whatever. So we have several layers. If we want to organize such a work, then you have some kind of portal. So the user should be authorized and authenticated through some service. Here is mentioned as an AI. Then you have some kind of research products already ready to use. And this research product could be anything. I will explain that later. And of course, if you go into this business down underneath, it's very complex infrastructure, because you have there multiple servers, multiple supercomputing centers, some complex management, and so on and so on. I'm not going to go into the detail here, but interestingly, before going there, I would like to highlight in astronomy how was the data history, how the data was accumulated. Like in Ptolemy's time, it was about 1,000 handful stars catalogized. This is one of the first, is Almagest catalogs. But then in about 1627, or in that time, there were also some Kepler catalogs. Or if you go a little bit further, then you have in Prodomus Astronomia about 1,500 stars. And already in 1900, in this locally here in Bonn happened, then you have in those catalogs about 360,000 stars. Mostly might be that in that time there were not every object as a star, because at some point they were discovered it could be also interloper or galaxy or whatever. But anyhow, this was not so much. Already in 19th, we had already digital sky survey like DSS. It's just previous version of this SDSS, which was started from 2000 until 2006. And you can see now the data size is rising rapidly, because the technological advancement in science was in that way that you are able to acquire more and more light from the sky. And you have new technologies like computers. You are able to catalogize them. Instead of putting on a glass plate, you put in a digital form. And then you can see already since 2000, we are working with terabytes data sets and over 100 millions of objects. In nowadays, since Gaia era, we are working with billion stars, and the data is going over the petabyte scales. So this forces us to organize in astronomy the data sets in special data portals or databases. Actually, astrophysical community is well known with data organization because they had a long history. They needed to catalogize every object, every observation during the research. So the astronomical databases are collected in this International Virtual Observatory Alliance registry. It's called VO registry. And in this VO registry, if you look, we have almost 300,000 services registered there. A number of registered services are growing up. Here you have, for example, like Gaia Archive, which is some satellite, Gaia satellite for non-experts. It's just satellite which was launched by ESO since 1903, and it's collecting light from all stars what he can find in our Milky Way. That means we are trying to get all possible visible stars within our own host galaxy. And this satellite is operating 24/7 daily, rotating in his axis and continuously scanning whole sky, collecting the data. You can imagine how much data is collected over these several 10 years or even 11 years. So to access those data sets, there are several protocols. And since Virtual Observatory is established in 2001, and this multi-wavelength astronomy was driving these standardizations, because if you have single wavelength, let's say visual part of the light, but if you have an X-ray or if you have a, let's say, ultraviolet range, which is not visible for human eyes, all those ranges to observe same object. For example, if you have a dust behind the dust of the stellar dust, you don't see objects, then you need to go to different wavelength. Let's say even in radio astronomy, you need to go with radio wavelength or with UV wavelengths. Then you want to search what kind of observations you would you already have for the given object. To do that, you need to have a standards, and these standards came out like continuously evolving, of course. Therefore, many standards in different branches is developed. For example, standards how I'm going to talk to this data, how I'm going to collect this data and label them. This metadata idea, how we are going to calibrate our units. This is stored in the metadata. Then how I'm going to access the data over the web interface, over the command line, over my web browser. Then you are going to develop protocols. And those protocols, such as table access protocol, this TAP protocol was enforcing us to develop further to make special SQL query language called ADQL, Astronomical Data Query Language, which is like a dialect of SQL. Based on that, you are talking to your database and getting your data. Once you have those protocols, you can glue all those services together within one registry. So you collect your data, put on that registry, and other researchers, they can search transparently over some portal or web interface and continue his work. So those IVA standard protocols, just to impress you, this flashy slide, how many standards, how many years. It took almost 20 years to standardize within the one consortium like astronomy to collect and get all standards together and synchronize them. Until now, it's very dynamically evolving, these old protocols. Some of them are outdated, some of them are in, but you can see it's not so easy task to bring this stuff together. If you look this IVA architecture, then how it works, this registry, that computers, they understand what users are asking to computers, then you need to follow several standards. And there's query languages, there are some file formats, and so on and so on. And providers, data providers, they need to keep track and keep their services up to date. Otherwise, you cannot query those data sets which are hosted in your site. So if you look data flows, how usual way that you have a planning, collecting, processing, publishing, keeping data in preserved form, and then trying to reuse that for future coming projects. But as you know, in reality, there are many, many in-between steps. If we go in more complex things, then all these steps are containing so complex stuff that where you store your data, how you keep your local information, what you share with others. This is extremely complex thing, how is shown in the right side. Okay, here we would like to show some kind of one example of cosmological data flow. Cosmology is an astrophysics field which tries to understand how our universe formed and how the objects are formed within this universe. To understand that, you are measuring background microwave. It's nothing else like you put some satellite in a space and measure in different directions temperature. And then you see in a temperature fluctuations. As you can see here, these WMAP temperature maps, they are improving by Planck telescope and so on. And this temperature fluctuation is a fingerprint of initial matter distribution when first this Big Bang was happening. Based on these initial conditions, you can predict how was initial matter distributed in a space. Based on that distribution, you put this data into the computer, into the supercomputer, calculate them, every dust particle or stellar dust particles coming towards each other's due to the Newtonian gravity. Then they're collecting each other's, and then bigger objects are formed. In the end, you have an n-body simulation which describes those structure formation. Now, to understand, is your measurements correct? Is your predictions are correct? Is your observations are following this Big Bang theory? Can you predict or reject this Big Bang theory? To do that, you need to produce many n-body simulations. Like here, you need to have millions CPU hours calculations. Then you need to have a storage space. This is only raw data. And what is the raw data? Storing 6D information. 6D means velocity, positions, and plus on top of it, mass each particles, and time and parameter space of simulation. Once you did that, you need to find the objects like these blobs are showing here. Is it galaxy? Is it supercluster? Then you build up merger tree and understanding this, how these objects were merged together. In the end, you get some kind of galaxy in the last time. So you need to catalogize them, put into the special database, and then publish this data with specific DOI assigned there. Once you did that, then you can access or provide access, for example, over our portal like Multi-Dark Bolshoi project. It's one of the largest cosmological simulations international organized between US, Europe, and so on, different collaborators. And these data sets now is public and you can access. You can see here is already one task, one simple from first of few way how I do my simulation and share with others. It takes years to prepare this. And this is not simple, but without this VO IVA standards, you couldn't build up such a web service. This is very important. Well, then if you go to another consortium members, there's not only so-called simulation people, there are also observers. So you have satellites, you have ground-based satellites, ground-based telescopes, you have satellites which are carrying the telescopes into the space, you have international connection, then you build the instrument, then you try to data process, then you make public the data. This data curation from A to B movement is very complex and very hard because for some observations you have also embargo time. You cannot publish immediately or give away immediately. You need to wait 6 months or 1 year and then give that away until the phase of data exploration. A similar situation we have in high energy physics. High energy physics, for example, you want to have simulation, you want to try in your accelerator find some kind of signals of that, let's say, new particle or new phenomenon. To do that, you need to have several steps, similar like in cosmology or in astrophysics or in observations. You organize your simulation, you build up a collider or accelerator, then you collect this data with supercomputer, curate them, and then you do individual analysis where mostly PhD students are required, of course, and then later you put them to publish. Of course, these all cycles, you have analyze, collect, clean, publish, curate. These are always like loops which are coming over and coming over. To organize this whole stuff is not so simple because of data flow and amount of data is extremely high. So I'm not going into detail how the life cycles in the physics is organized, but it's very, at some point, it might be very messy and very complex. But what I want to emphasize here, if you have some specific infrastructure, it doesn't mean that if you collect the data, make really research data management correctly, use proper tools, these last points are becoming mostly invisible for these infrastructure people, but for scientific personnel, it's very important. These last dirty miles are called. What means if you have a student or time-limited project, what I'm going to do with this data, which is left, this leftover data, this to manage is also another problem because some of them, it might be very complex and very useful for the future projects. Some of them you need to just throw away. And this is an unsolved problem, for example, how I'm going to deal with these leftovers of the data. Besides that, what we thought, okay, this all complex stuff, data curation is complex, data collection is complex, and different consortium members are thinking differently, but what all of us is connecting is very important thing. If you have some platform here mentioned in the middle, which is connecting all these complex stuffs, like if you have a storage, if you have a computer resources, if you have results where to store, and then if you have a home institute which is telling you, you are my coworker, you are working at Home Institute, you are allowed to use these resources. If you collect this old stuff, is it possible to organize some kind of workflow environment where you can save this your workflow and give away this workflow as a digital research product, some other person from the community, and then he can, from different community, they can, using this platform, they can run this stuff easily. This to organize, that was our goal, to make federated infrastructure. Okay, to build up federated infrastructure, what you need to have an idea of what is the research product in your case. Research product, we are thinking like such a black boxes here in the left side, what you see stored in the registry. It's nothing else like you can imagine, where you have information, your publication is inside, your software is inside, your data sources where come from data to produce this publication. Then you have a metadata which describes which protocols they can talk to you. Then you have maybe possibility, if some user wants to go through the portal is a web interface or some software, and click on this digital research product, and this will be open, and then you can continue from that point your work. Is it possible or not? For some cases, probably it's not possible. If you have a petabyte data, you cannot put data sources, but you can put how to access that data. That means this all data resources providers, they need to follow standards. So once you have that, you can use this digital research product and provide to other your coworkers. One of them is this RIANA environment. For example, this RIANA is developed by CERN group. It's very heavily used in the CERN. And this is some kind of software platform which allows you to run workflows with the mind in the back, in your head. It should be reproducible. That means if you have an experiment and you store all parameters and data sets within that experiment, then later, if some other person comes, he can reproduce your results. And if you combine this RIANA, if you combine with this digital research product idea together, then you can actually bring into the life for the researchers, bring this very easily and bring all your coworkers into your project. So this digital research product standard is not yet standardized. It's just ongoing project within the Punch. And you can see we started in 21 and it's might be take more time than to make this standard. We know from IUVA in astronomy, it took almost 20 years to come up together within one community. And now we are trying to glue several communities together, which is not a simple task. So actually this complex stuff I will leave, but what I want to mention now, okay, if you have a now idea of how your digital research product is constructed, how you are going to run this digital product, now you need to have environments where to submit your jobs. This is this Compute for Punch branch is responsible for that. And this Compute for Punch is like headed by KIT, Karlsruhe Institute of Technology group. And you can see this is some kind of connection between many data centers, supercomputing centers. There are special job management system, which can connect to different technologies. And this Cobalt TARDIS is some kind of scheduler. He's decided if you have some job submitted into this system, he decides, oh, where the system is not loaded, where we have our resources, let's send this job over there. And this to organize is extremely complex. I'm not going to into the detail how to organize this workload or how to talk each services to another one. But important thing, what I want to mention is IA based. That means you need to have one single sign-in portal or key, and using this key, you are able to use these all resources. Well, to organize this old stuff, what you require technologically, you need to have a continuous integration, continuous delivery workflows. This is some kind of in IT well-known processes. You need to have some container registry, and this container registry, the containers is a special technology in informatics or in programming environments where you put your old programs in one closed, you can imagine like zip file. You put in a zip file all your components, what code needs, and you put this zip file everywhere. Doesn't matter, is it Windows, Mac machine, or supercomputer, and your code works. And this technology is used everywhere in nowadays. And we are using this technology to distribute the software between different groups. And one of the important points, every point you see this Rihanna. This is this workflow manager. And I will explain about Rihanna a little bit more. But before going there, we need to have this storage for Punch. That means you have a code, you have a project. Now you have a place where to execute this stuff. This is compute for Punch. Now the next phase is where I'm going to store my data and how I'm going to access the data. Because it could be not all data sets what I'm currently analyzing in DAISY or in Karsu or in GSI are publicly available. That means you need to develop further Dcache or Xterroot special technologies to gather this data, take into account, are they allowed to be accessed by you or by your coworker or by your digital research product, yes or no? And there, of course, different protocols are involved there for Compute for Punch. And this is also quite a complex infrastructure, and we are proud to say currently now in our environments, this Compute for Punch, storage for Punch, they are quite nicely coordinated and they are working together. So you are getting one key, this is your token. Based on this key, you are allowed to access to Compute for Punch and storage for Punch. Of course, there are several security implications that your keys expire every 7 days. You need to renew it. That means you need to log in, generate your key. That because it's also many security considerations are around. Okay, now we have all components together. You have some researchers, they want to access these data sets from storage for Punch, use Compute for Punch resources. Now, time to run the job and protocol that. This to organize what we have at AIP, actually, we have a copy of same environment, almost little bit more advanced environment that what in a CERN was used. We have this Rihanna software we developed with Rihanna developers further to be able to run not only in the CERN, rather than to run in our infrastructure. You see here we have several storage, we have special Compute for Punch S3 storage. This is some technology which is like 90% of internet is using S3 storage because of Amazon AWS services. Every big cloud players are supporting S3 storage. We are doing that as well. But the storage is hosted in our hardware at AIP in a cave. So in a cluster room, that means we are in a safe side. Once you have this infrastructure, you access to your Rihanna P4N AI PDE. What you get, you have some kind of web interface. You click by one button, put your password from your university, and you end up with this interface, web interface. To run your jobs, you can have or some buttons predefined from your colleagues, like a launch button to run your job there, or you can go by command line in terminal Rihanna client, and then you submit your source code. There are many examples how to do that, and this is organized in that way. Every time when you run the job, it's unique, and if you go to a web portal, you can see, is this job finished, failed, and then you can go in and see the results for this workflow. And each workflow is isolated as it is. So there's one interesting integration with Rihanna. You can even have a web browser running or Jupyter Lab running within the Rihanna, and you could have here even desktop within the web browser, which makes life easier for non-command line experts. And this is very nice. That means you can run any workflows in this environment. Well, I want to finalize now my talk concerning to the NFDA for Punch infrastructure. We have now a possibility in our consortia. Doesn't matter, is it astronomer, is it a particle physicist, or a high energy physicist. All of them, they can run workflows using our infrastructure, using this Rihanna workflow manager. And then we have several services, like we have own GitLab IPDE, we have special Kubernetes compute environment, and the users, they are not interacting directly to this lower level that what you see, this S3 virtualization, storage, or hardware. This is question of local administrators, but what users are interacting is this Rihanna or own software which runs on our Kubernetes. And this is making life easier. And once you have these reproducible workflows, then you can start thinking, okay, how I'm going to build this digital research product that everyone can access that. Thank you very, very much for your attention, and I'm open for the questions.